So let me try to explain the physical meaning of Ampere's law in English and in Chinese once. So, um, so in English. So actually, the physical meaning for this one, okay, the line integral, it turns out it will be a scalar. Of course, mu zero I is a scalar, and similar to Gauss law, you want to find the E field using Gauss law. So you need to depend on the symmetrical. You need to rely on the symmetrical because when you calculate the electric flux for Gauss law, then you can simply count the charge inside the Gaussian surface, and then you don't really need to do the double integral. And according to symmetrical, then you can assume every point on that surface is the same, so that okay, you can calculate the E field at every point on the surface. And similar for this case, we want to know the line integral B dot ds over this contour or ambient loop. And if there are some types of symmetric, something like that one, you have only one current, so that you know the magnetic field is rotation with respect to that curve. And in that case, you don't really need to calculate the line integral. You only need to count what is the current, what are the currents circulating by that ambient loop. For that one, only I, and for that one, I1 minus I2. So for that one, there are no symmetrical, so you can only calculate the overall line integral for ds dot ds, b dot ds. But for that one, you know that it is symmetric. So every point, the magnetic field at every point are the same. So you can simplify the line integral, something like that. Of course, if you have a computer, you can use the numerical method to calculate the line integral. But usually for hand calculation, you usually assume B will be uniform over that contour, or we need to design some special case so that you can calculate the line integral. I don't know, it would be very strange. So for that case, we can simplify B dot ds and line integrals to be something like b times 2 pi r equals to 0I. Then we can find that B will be mu 0I over 2 pi r. And of course, the direction of the magnetic field should be determined by the right-hand rule. For that current is pointing out of the plane, so the magnetic field should be counterclockwise. Okay, it should be something like that. So I recap it in Chinese. 那安培定律的话，其实跟高斯定律就蛮像的。高斯定律其实是算那个电通量，它是需要那个对称性的。如果你有对称性的话，那我只需要算右手边是那个高斯面所包围的电荷，那除以 F0 就是那个电通量。那有对称性的话，我们就可以假设说整个高斯平面上面的每一个点都是一样的，那我就能够取出来那个电场大小，那方向的话就是由那个电荷的正负决定的。那这边是类似的，这边是类似的， 按培定律左边就是一个线积分，那我不想算这个线积分，那我就数这个 Ampere loop 所包围的电荷。那按照右手定则，它是反时的方向的，那出来就是正，进去是负。那个例子就是说 I 是出来的，所以右手边就是 μ0I， 所以我们可以右手边写 μ0I。那这个是有对称性的，那我们就可以写 d 那个先积分 b 到 ds 就可以写成 b 乘以 2πr。那个例子的话，就是 I1 是出来的 ，I2 是进去的，那我们就可以写出来是μ2括号 I1 减 I1 减 I2，然后右手边就可以写出来，但是那个就不对称的，所以那个你就是单纯只是把那个线积分算出来而已，你就没办法算每一个点是怎么样。Okay. So actually, the physical meaning for this line integral is something like, according to the defined Ampere loop, how is the field rotation in that direction? So for electric flux, when you calculate the electric flux, the physical meaning is something like how does the field flowing out or flowing in? If it is positive, it is flowing out. If it is negative, it is flowing in. For here, if this line integral is positive, which means the field like rotating counterclockwise. If this line integral is negative, the magnetic field is something like rotating clockwise. So let's come back to the sample example. Okay. So for this one, the cross section of a long conducting cylinder with inner radius A, and outer radius B, the cylinder carry a current out of the page. So this is out of the page. And the magnitude of the current density J is given by CR squared. What is the magnetic field at point that is 3 cm from the central axis of the cylinder? Okay, so this is 2 cm, 4 cm. So it asks you the magnetic field at 3 cm. So first of all, we need to calculate the I enclosed. So I enclosed is something like J dot dA. Flowing out of the page. Okay. Flowing out of the page. Okay. So J is flowing out of the page, and actually this Ampere loop is defined to be clockwise. So actually the positive direction of this loop should be into the page, and into the page means it will be positive current. Positive current will be pointing to the page. So here, so this one should be negative. dr square dr. Sorry. It should be something like
CR square. And actually, dA is R dr d theta. I've mentioned this previously. So we times R dr. And also we have d theta. Theta is from 0 to 2 pi in polar coordinate. And the lower and upper bound for dr should be from 0 to 3 cm. 3 cm. How do I denote it? Maybe we write r, or we can use it r prime, r prime, r prime. So it's just a notation. So nothing special. So this is r cube, and actually it will be something like 4 c over 4 r to the 4th power. Sorry, this one should be from A, because inside there are no current. So this one should be A rather than 0. This one should be A. Okay. So here should be R to the 4th power minus A to the 4th power. So for this one should be 2 pi. This 2 pi. So we cancel the 2. So it will something like pi over 2 c r to the 4th minus a to the 4th. So actually, according to the Ampere's law, B dot ds would be mu 0 I enclosed. And so B, maybe I just insert another page. So I just insert another page. So just now we have B dot ds equals mu 0 I, and for the left side B times 2 pi r, because it is symmetric. So we can write it like this. This is I enclosed, so mu 0 times minus 2 pi c pi, sorry, not pi, r to the 4th. R to the 4th power minus a to the 4th power. Something like this. So finally, we can write it as B equals minus mu 0 c 4 pi r to the 4th power minus a to the 4th power. Okay. Sorry, this 4r. Oh, this one should be r rather than pi. This one should be r. This one should be 4r. 4R because pi is cancelled. Pi is cancelled. So here we have 4R on the bottom. C on the top, mu0 on the top, and this one on the top. So this should be like this. So finally, it will be something like minus 4 pi times 10 to minus 7. C is 3 times 10 to 6. 3 times 10 to 6 over 4. R is 3 cm, 0103. And here 0.03 to the 4th power minus 0.02 to the 4th power. So finally, it is minus 20 mu t Tesla. And the direction for this is counterclockwise, because the Ampere loop is clockwise, and the Ampere loop is clockwise, and B is negative, so B is counterclockwise. Any questions? 第一步的符 ，OK, this one. Okay, the negative sign comes from, okay, so the Ampere loop is defined clockwise. So according to right-hand rule, positive current should be going to the page. But the J into the page, right? So for the second line here, carry a current out of the page. So the current should be negative when you consider this Ampere loop. If you assume the Ampere loop to be positive, then J will be positive, and you find out and the final answer B will be also positive, which means which also means this conclusion. B will be counterclockwise, because at that case, if you assume Ampere loop to be counterclockwise, and then you find out B is positive, so B should be counterclockwise, which matches this one. So it doesn't really matter if you assume the Ampere loop to be clockwise or counterclockwise. If you can manipulate the positive or negative side correctly, the answer should be correct. Any questions? Okay. So this one is about the solenoid, 线圈. So we talk about the magnetic field generated by a solenoid. The solenoid's magnetic field is the vector sum of the field produced by the individual turn, or we can call it windings, that make up the solenoid. So you see this is something
range. So you can something. So for that one, I is something like that way. So you can use the right hand to do something like this. So you can determine the magnetic field inside the solenoid using the right hand rule. And actually, you can feel like so here should be close to this wire. So this part should be dominated by this wire, but not the other. So actually, this is cross, which means the current is going in here. So the magnetic field here, this part should be something like this. And so as this one, and this one, all of them are rotating clockwise. For that one, because this one is going out, this one going in, this one going out. So for this part, the magnetic field are rotating counterclockwise. However, for that part, they are relatively far away from this one and that one and the others. So the magnetic field here are contributed by all of them. And actually, so most of the magnetic field in this direction will be cancelled. And the only magnetic field component will be pointing in that direction. And for outside the solenoid is something like that, something like a magnetic dipole. For point very close to a turn, the one behaves magnetically almost like a long straight wire. So like let's talk about this part. There are almost concentric circle. And the direction you need to use the right hand rule to determine the direction. The field tends to cancel between adjacent turn, which means at this gap, this is almost zero, because according to what we mentioned for the magnetic field line, if it is dense, which means the magnetic field is strong. If it is not so dense, the magnetic field is weak here. And actually, at this point in the middle of the two wire, actually this one is pointing down and this one pointing up, and they cancel each other. So the point between every two wire will be very weak or even zero. At the point inside the solenoid and reasonably far away from the wire, B is approximately parallel to the solenoid axis, which means this way. This is what we call the solenoid axis in this direction. So a section through a portion of a stretched out solenoid. So actually, we can use the Ampere's law to find the magnetic field inside the solenoid. So according to Ampere's law, actually we need to assume that B is uniform inside and almost zero outside. Actually, the magnetic field outside the solenoid will be quite weak, although not zero. But actually here we make this assumption, the uniform, it is uniform inside and zero outside.
And using a rectangular impedance loop, A, B, C, D, A, B, C, D, so that A, B, C, D, so that this is the original line integral over the impedance loop. So we can separate into from A to B plus from B to C plus from C to D plus from D to A. So this one, this one, this one, and this one. Okay, actually we know that from B to C here, the magnetic field is perpendicular to this line. So the inner product of B dot ds is 0. So this one is 0. And also for C to D, because we assume the magnetic field outside is 0 also. So this one is also 0. And from D to A, similar to from B to C, this one is perpendicular to the magnetic field inside the solenoid. So this is also 0. So within these 4 terms, 3 of them are 0, and the rest of them is only from A to B. And actually, we assume B is uniform within it. So it is nothing but B times the length of this segment, and this is small h. So this one is nothing but B times h. Any questions? Okay, pretty simple. So we have the left-hand side of the impedance law to be B times h. And for the right-hand side, okay, we need to calculate the current going through this loop. This loop is counterclockwise, so we need to count the current going out of the page, because it is a solenoid. So if you just cut the solenoid in half, so for the top ones, the current is flowing out of the page, and for the lower row, the current is going into the page. It's something like, because it is a solenoid, it's something like the current is going from here to here, and then to here to here, something like this. So actually, this is something like this. I cannot write it too dense, otherwise it will be something like this. But actually, it's something like that. So you try to make the wire going like this. So in this case, the total current going through this Ampere loop is something like I times n times h. Small n is the number of turns per unit length. So actually, we can write it for the left side, it is BH. For the right side, it is mu. I enclosed is I and H. And H is cancelled. So the rest of the stuff is B equals mu 0 I n. N is the turn per unit length. Which means if you want to generate stronger magnetic field, we need to make the solenoid as thin as possible. You hope to route more and more winding in unit length. And of course, the other way is to increase the current. U0 is of course constant. 左右，因为垂直啊。B dot ds 啊 ，ds 就是 ds is something like this. ds for BC, ds is something like this. You're going through the loop. For this part, ds is something like this. So B is perpendicular to ds for BA and BC. So this 2 is 0 because these two are perpendicular. And for this part, it is outside. So B equals 0 outside the solenoid. So this is 0 with different reason. So the only non-zero part is this one. Okay, so the physicians like to make things something like very strange. So with the solenoid like this, they try to connect the front to the end. So it will be something like a ring, something like a ring, something like this. Okay, you try to imagine yourself because the figure is showing like that. Okay, so it is called the toroid. Toroid may be described as a hollow solenoid that has been curved until two ends meet, forming a sort of hollow bracelet, 就是手链. But it is hollow because when you cut it out, it is a solenoid. So it is hollow. 空心. Okay. So from the symmetry, we see that the line of B from the concentric circle inside the toroid direct. Okay, so actually the magnetic field inside a toroid will be something like this. So actually, we can also use the Ampere's law to find the magnetic field inside the toroid. So similarly, on the left side we have B times 2 pi r. R is from the center to the Ampere's loop, the radius of this Ampere's loop. And for the right side, mu 0 times I enclosed. I enclosed is the I for the toroid times capital N. N is the total number of turns. Because as you can see here, the current inside the loop is already pointing into the page. Out of the page. Maybe you need to check your size. Okay, actually, all of them across, so into the page. These are out of the page. So all of the current are going into the page. So the total current going through this Ampere loop is simply I times capital N. N is total number of turns. So in contrast to the situation, so we can divide 2 pi r on both sides. So B is something like mu 0 I times capital N over 2 pi r. In contrast to the situation of a solenoid, the B is not constant over the cross section of the toroid. So this is not constant. If it is closer to the center, it is stronger. If it is far away from the center, it is weaker. Because if you can simply imagine that this loop is dense, more dense, so you can see a gap between the outer loop. So of course here will be weaker. The magnetic field close to the outer loop will be weaker, which matches the intuition. Any questions? Okay. So sample problem. Solenoid has a length and a diameter. It carries a current. It consists of 5 closed packed layers, each with 850 turns along the length L. What is B at the center? So actually, B will be mu 0 In. So mu 0 is nothing special. Mu 0 is only a constant. I is already provided there, 5.578. So what is small n? Small n. Oh no, we can directly substitute the number in it. Okay, so mu 0 is 4 pi times 10 to minus 7, and I is 5.57 ampere. So what is n? N is something like here, 5. So we have 5 closed pack. So we have 5 times 850. And actually, 850 turns along the length L. So, the turn for unit length should be divided by 1.23 meter. Which means totally it is something like this. This is L. And it consists of 5 pack and 5 pack. Each of them have 850 turn per L. No, it should not be like it. Oh, they are in parallel. It should be like that. shouldn't be like that. It should be something like should be something like this. 1, 2, 3, 4, 5. This is L, and this is 850 per L. So this one should be like that. And finally, the answer will be 2.42 times 10 to minus 2t. So here we talk about current carrying coil as magnetic dipole. So actually, we can regard a current carrying coil. Actually, it is equivalent to a magnetic stick, and it is actually a magnetic dipole in a physics point of view. So actually, this current carrying coil is equivalent to this stick, and the magnetic field generated by this coil is given by this equation. Mu0 over 2 pi times mu is the magnetic dipole. Magnetic dipole is the number of turns times the current times the area of this coil over this C cube. C is the this direction. So here mu is the dipole moment of the coil. This equation applies only when Z is much greater than the dimension of the coil. So Z should be much larger than, maybe we can say R. Z is much larger than R. So it is something similar to this one. The electric field generated by a magnetic dipole, by an electric dipole. So you can see mu0 over 2 pi. This is 1 over 4 pi epsilon 0, and well, actually you can reduce it. So 2 pi epsilon 0 and mu0 are something like one is on top, one is at the bottom. And this is the magnetic dipole, this is the electric dipole, and Z square. So they have almost the same form. So we can also say that there are two ways in which we can regard a current carrying coil as a magnetic dipole. So its experience a torque when we place it in an external magnetic field. So if this coil with current and the magnetic field going this way, so this coil will rotate with respect to this axis. And the next one is own intrinsic magnetic field given for the distant point along its x-axis. So these two are actually the same. So we can similarly derive the magnetic field generated by this coil. So we use the law of Biot-Savart. So for this point, ds is pointing out of the page, and r is in this direction. So ds plus r should be pointing to that direction. And alpha is this angle. So actually, dB perpendicular will be cancelled with this one. Okay, for this one, maybe we call it ds prime, which is pointing into the page, and out in this direction. So ds this way and cross. So you have dB generated by this part should be something like this one. And actually the perpendicular path, so the dB perpendicular is cancelled. The only part remain is the dB parallel. So all of the magnetic field generated by this coil should be pointing upward. And so mu0 I over 4 pi is simple. So we have cosine alpha. Cosine alpha is this one is alpha. So this one is alpha. So dB parallel should be dB cosine alpha, because this one over this one should be cosine alpha. So we have cosine alpha ds over r squared, because this is unit vector. So this is 1 times ds times cosine alpha. And we have r equals this one and cosine alpha equals this. So we substitute all of them into the original equation, and then we take the integral so that we can get the overall magnetic field. And actually this is constant over ds. So all of them are factored out, and integration of ds is nothing but 2 pi r. So 2 pi is cancelled, and this is r squared. So as I mentioned, we also assume c is much larger than r, so that this one can be ignored, this term can be ignored, because when z is much larger than capital R, then c squared plus r squared is nothing but z squared. And we take cube and square root, so c cube. So we finally have this one, and we multiply pi on the bottom and the top, and actually this is the area of this coil. So we can write it as IA, and actually IA is what we define the magnetic dipole. So it can be rewrite as mu. So finally we can derive the magnetic field generated by the coil, something like this. And if the coil have multiple turns, the mu would be capital N times IA.